Gives me an immense pleasure to present our esteemed Director of Admissions, Dr. SSM Abdul Majid sir, a fervent advocate for education and an intelligent champion for our student body, to deliver the felicitation address.
Dear students, and the guest of the honor today, Dr. Mohamed Aejaz, the head of the department of our prestigious polymer engineering, Dr. Samshad Begum, and the faculty members. It gives me immense pleasure to associate with all of you today for this wonderful program of our department, that is the Polymer Engineering Across Borders, a global alumni webinar series. So in the series, this is the third lecture. In the previous lectures also, our alumni, those who are holding a very high positions in different organizations, they delivered a very nice lecture. It was highly useful for both the student as well as the faculty of our department. In this respect, today we are organizing this wonderful lecture by this Dr. Mohamed Aejaz on the topic Polymer Membranes for Gas Separation. Actually, students, you are learning so much the technology, science and technology about the different polymeric materials, starting from plastics, rubbers, composites, so on. But when coming to the applications of this polymers into varieties of diversified field, the polymer membranes are playing a vital role in the technology development in many areas. Especially this polymer membranes used for gas separation, it is highly useful for the most of the recent technology, where we require the separation of gases according to its nature, quality, and chemical structures. On this connection, this topic is very relevant to all of us today. I'm very happy to welcome the guest speaker, Dr. Mohamed Aejaz. It is a proud moment for me to say that Aejaz is my student. Aejaz is a student of this polymer engineering department. Actually, when he was a student in the department, while learning the program, Aejaz was a highly motivated student. I can remember the things which the technology as well as the other things we discussed in the laboratory as well as in the theory classes. He was very studious student. He was highly attentive in class. So I can, in my observation for the past 37 years in the campus, a student when a person when he was a student, when he was active, definitely in the future also he will have a dynamic positions. He will access all kind of success in the life. So Dr. Mohamed Aejaz also growing like anything. I take this opportunity to appreciate him as well as wish him to reach even a great higher position in the future also. I wish this seminar, that means the polymer engineering across the border, the program, have all success. Thank you.
Thank you, sir, for your felicitation address. I now respectfully invite our esteemed Head of Department, Dr. S. Samshad Begum ma'am, a luminary in our academic journey and a steadfast pillar of our collective success, to grace the occasion with a welcome address.
Good morning, all. It is my distinct pleasure to extend a warm welcome to each and every one of you joining us for today's webinar, Polymer Engineering Across Borders, a Global Alumni Webinar Series 3. We are truly honored to have with us the speaker for this session, Dr. Mohamed Aejaz, Head of Thermal Analysis at Covestro, Germany. Dr. Aejaz's expertise in the field and his invaluable insights into polymer membranes for gas separations will undoubtedly offer profound perspectives and inspire all of us. I would also take this opportunity to welcome Dr. SSM Abdul Majid, Professor and Director Admissions. His vision for the future of engineering education continues to thrive excellence within our institution. His continuous efforts to enhance the admission process and attract the brightest minds are integral to the continued success of our academic community. A special thanks to Mrs. R. Daulat Banu, coordinator of this event, and our faculty members. I would also like to acknowledge the efforts of our student coordinators, Mustaq Naina and Muhammad Fazil, whose enthusiasm and commitment have been pivotal in ensuring the smooth execution of today's event. As we begin this exciting session, I encourage all the participants to actively engage, share your thoughts, and contribute to the rich exchange of ideas that makes this webinar impactful. Thank you once again for joining us, and I wish you all productive and insightful experience throughout this webinar series 3. Thank you all.
Thank you, ma'am. Now I request the faculty coordinator, Mrs. R. Daulat Banu, an enthusiastic motivator to set our student community, to introduce our distinguished chief guest for the day.
Good morning to one and all present here. I am glad to introduce our alumni 2012-2016 batch, Dr. K. Mohamed Aejaz, Head Thermal Analysis, Covestro, Germany. He has graduated B.Tech Polymer Engineering in B.S. Abdurrahman Crescent Institute of Science and Technology in 2016. He completed MS Polymer Science in 2019 and PhD in Experimental Physics in 2023 in Technical University of Berlin, Germany. His PhD thesis titled Structure and Dynamics of Bulk and Nano-Confined Ionic Liquid Crystals. Dr. Mohamed Aejaz started his career as Research and Development Engineer in Shimla Paints, India in November 2016. Then he continued as Master Intern Polymer Rheology and Processing in 2019 and continued as Master's Researcher in Technical University of Berlin, Germany. From July 2022 to September 2023, he worked as a visiting researcher in Institute of Physics, University of Mainz, Germany. Currently, he is holding as a position as a head thermal analysis Covestro, Germany. He has enormous experience in material characterization using dielectric spectroscopy, nanocalorimetry, and X-ray scattering techniques. And he has led a new direction of computational research to support the experiments. He has published 15 research articles in the areas such as molecular mobility in high-performance polycarbonyls, plasma deposited copolymer films, microscopic dynamics of highly permeable superclassic polycarbonyls, self-assembly of ionic superdiscs in nanopores, molecular engineering of supramolecular polymer adhesives. He has made several technical presentations in USA, Spain, and France. He has received many awards and honors. Out of 25 PhD candidates across Europe, he was awarded for P&G European R&D Seminar at Belgium in 2023. He also got BASF International Summer Course, which was awarded out of 50 PhD candidates at Germany in 2022. With this, I welcome Dr. Mohamed Aejaz to deliver a lecture on the title Polymer Membranes for Gas Separations in this Alumni webinar series. Thank you.
Now, let us all listen attentively to the insightful address by Dr. K. Mohamed Aejaz, sir, our esteemed chief guest, as he shares his thoughts on the title Polymer Membranes for Gas Separation. We encourage you all to actively participate, and we will have a Q&A segment towards the end, where our chief guest will address your questions.
Thank you so much for introduction from all the sides. Now, so thank you, Majid sir, for introducing me and remembering me as someone who was very active, and also to Shamshad ma'am and Daulat ma'am for explaining the CV in a very, very detailed manner. So what I'm going to do is, so the idea would be that I'd make a slideshow. So what I'm going to do is I'm just going to give you guys an overview of how polymers are used in gas separation and what kind of polymers do people use for gas separation applications, right? So you don't have to remember anything, chemical structures or anything. This is going to be a broad overview just to give you an idea. So this is going to be a broad overview just to give you an idea how polymers are utilized in places where you're going to use membranes and other applications. So if I can share my screen. Okay, do you guys see screen?
Yes. Yes. Yes.
Yeah, okay, good. Good. So this is going to be the talk as already a lot of people introduced. So polymers for gas separation membranes. So it's always a tale of permeability and selectivity. And I'm going to tell you what that means in a couple of seconds. So a little bit about me. I think Daulat ma'am introduced very clearly what I did, but it's the same thing. I'm just going to show you in a slide. So I started studying BTech polymer technology. It was known by then. So it was polymer tech. And I completed in 2016, moved to working in an industry at Sheenlack Paints. And then I decided I wanted to do, and then I moved to Germany. Things happened. So I moved to Germany to masters in polymer science, not engineering, because when I was working in Sheenlack, I realized I might not be a very good engineer, but I really wanted to do science. So I decided to do polymer science. And from there, I ended up getting a PhD in soft matter physics or experimental physics, doing mostly fundamental stuff that might help engineers in the future to design better materials, which then lead me to get an industrial position as a lab head in Covestro. So Covestro makes polyurethanes. I mean, that's one of the products that we sell globally, and we also have an office in India. So first question, before we even start discussing polymers for gas separation, one of the questions that you should always ask is, why do you want to separate polymers, right? I mean, why do you want to separate gas separation at all? So here's an example of carbon dioxide, right? Because carbon dioxide is a major greenhouse gas responsible for climate change. And this is contributing to a lot of environmental issues. And scientists have been always trying, I don't know, since 5 decades to somehow recycle carbon dioxide or capture carbon so that they could be, make our environment more green, more efficient, and so that people in the planet can live happily. So if you take a flue gas, which is a waste gas that comes from an industry, this is always a mixture of gases. So it's not a simple gas that the industrial waste produces, right? So you have carbon dioxide that goes anywhere between 10 to 15%, and then you have nitrogen that's like 70%, oxygen that's 5 to 10, and then you have rest is water vapor. So water vapor is not an issue, nitrogen is not an issue, because oxygen is not an issue because they are all present in your atmosphere, like in your surroundings and stuff. But what is problem is the carbon dioxide, right? So if you want to separate carbon dioxide from the rest of the gas, this would require using traditional chemical engineering unit operations. So that would mean you would use absorption, you would use cryogenic distillation. But the problem with these techniques is, I mean, they are traditional, they are efficient, but they are very energy intensive and costly, right? Because if you're considering distillation, so if you remember your basic organic chemistry class, distillation is anything but you do with the columns, right? So if you imagine that on a plant scale, so you're having multiple columns spread across, so that's really massive and that's really energy intensive. So what people thought since decades is that if we could use polymers, then we have a low energy alternative that could somehow selectively allow things that we want to filter from the rest of the waste gas. So that's the whole idea of why we do gas separation at all in the first place. So we have a target, we want to separate A from B because A is bad, or because you are interested more in A because A is recyclable or anything. And membrane technology exactly provides you this alternative to selectively separate your choice of gas from your feed. And here is a polymers for gas separation. So before I show how a membrane look like, this is a biogas plant. So if you want to separate a biogas, this is how huge your plant would look like. So if you see these domes, they are big. But if you were to replace it with membranes, you would have a plant that looks so small because all your membranes are modules. Like they are cylindrical modules that you could mount in a station. You could remove them once they are used, and then you could remount it back. So you are downscaling a big recycling or a biogas plant down to some number of modules that are very efficient in separating and doing the same process, right? So that's our idea. And that is what it is. So you go from a large scale to a small scale when you install a membrane, and then you would essentially upscale or downscale the process, what you want to do. But how do these membranes look like, right? I mean, I showed you a nice modules, like they are all modules installed here. And then this is how a single module would look like. And inside these modules, you have these hollow fibers that have your membrane material coated on them. So if you would again go down to look at the nanometric size, you would see that these hollow fibers look like in a cylinder. So it's a torus essentially, and then on the top of it is where your polymer membranes lies. So it's a very, very thin layer, less than 1 micrometer, and then it's loaded on a hollow fiber. So this 1 micrometer layer is what separates the whole gas that you wanted to achieve at the end, right? So if you have questions in the middle, just interrupt me. But how do they work, right? So yeah, we saw that you have a membrane. They come in modules. You could install them and do anything. But how do they work? It's a very simple process. So it's a solution diffusion mechanism. So first, imagine you have a mixture of gases. So the blue spheres here, they could be gas B, and the red are gas A. And then you are interested in separating blue from the red. So then you would pass this. So it's usually called the feed side. So so this is your gas feed that you would pass through on the membrane, and then this initially dissolves at the membrane side, and in step 2 it diffuses through your membrane, so and along the direction that of your interest, and then you have a membrane that's of a particular length, and the diffusion is directly related to the thickness and the direction that you're looking at, and at the end you have the effusion of your gas molecules that then you have the blue separated from the red, and then you're happy, right? So these are thin selective layers that allow certain gases to pass and certain to retain. So that's what this is, the whole process is like. So it's called solution. So you have a sorption, and then you have a diffusion, which is basic Fickian diffusion. This is a Fick's first law diffusion equation, if you remember this. And then your diffusion is directly related to the concentration gradient, and the whole flux then depends on it. And then you have a desorption. So very simple, right? So 3 steps. You have sorption, diffusion, and then desorption. Now, what happens, and what do we mean permeability versus selectivity trade-off, or that I wrote in my title, right? So I wrote permeability versus selectivity. It's a tail. Why? Because if you want to make a membrane out of a polymer, so what should the polymer look like, or what should the polymer possess, right? So the key properties is permeability. So it should let the gas molecules to pass through it. So if the gas doesn't pass through the membrane, then there's no point of using the polymer for this application. Selectivity. So it should be able to choose the right gas to pass through. So if you're passing carbon dioxide and a mixture of methane, you should be able to filter out carbon dioxide from methane. If it allows both carbon dioxide and methane, then again, the whole point is gone. And then it should be mechanically and thermally stable, because if you're going to put them in application, they are going to get degraded, corroded, and they're going to face harsh environmental conditions. So they should be stable. And then main is chemical resistance, because depending on the application, because membranes are very, very sensitive to corrosion and other factors. So what has been traditionally used is 2 types of polymers. So you either use a glassy polymer or you use a rubbery polymer for this application. And what do I mean by that? What do these terms even mean, right? What is a glassy? What is rubbery? So it's very, very simple. If you have a polymer whose Tg is way, way, way above room temperature or above room temperature, then it's a glassy polymer. Okay, so best example is polystyrene. The TG of polystyrene is 100 degrees, right? And it's glassy because its TG is above room temperature, it's brittle and it's glassy. And if you have a polymer that's way, way, way less than room temperature, then it's rubbery. So best example is polydimethyl siloxane. So these two types of polymers have two different microstructure or a molecular structure, if you wanted to look. So what happens in glassy polymer is you have voids in glassy polymers. What you have this empty spaces, so that you have a low free volume, but these free volumes are frozen because when you have a polymer in a glassy state, you have atoms or molecules in your polymer that are frozen in motion. So you end up creating low free volume, but they are stiff, they are rigid. So what happens is, because this free volume is low, you have low permeability because the gas diffuses through the free volume in your polymer. So imagine you have a noodles-like structure and then you have pockets in noodles everywhere. And if you pass the gas, then the gas will usually go through the pockets in your noodles and then it go. So in a glassy polymer, since the structure is frozen, you have this, the space allowed for the gas to go through is really, really less. So then you have moderate permeability, but then it comes with an advantage because you have high selectivity, because one gas molecule could go through the void, the other cannot go through the void at the same speed, because you have, so the carbon dioxide has a different diameter compared to methane. So that's why carbon dioxide would diffuse faster compared to methane. And this comes with an advantage that you have the glassy polymer allows you to have high selectivity. But in rubbery polymer, it's the other way around, right? Because rubbery polymers are flexible. Rubbers are flexible. Why are they flexible? Because they are above their glass transition. And once you surpass the glass transition, your chains become mobile. Your polymer structure is really flexible. And that leads to high free volume. Because so you have to remember one thing. When you, there's something called Brownian motion that would happen in all kinds of material, regardless of the temperature, is that your molecules or atoms in your material will always fluctuate no matter what. They will always try to fluctuate. And the same happens in a rubbery polymer. So your chains try to fluctuate and they have high free volume. And this allows more and more permeability, because now the gas molecules have a big space to explore. So you could have more gas molecules passing through, but then it comes at moderate selectivity, because since now we have, so imagine now you have more space, then both carbon dioxide and methane can go through simultaneously. So this reduces selectivity. So this is the permeability selectivity trade-off. So if you have one that's high, then the other goes down, and vice versa. And what happens is, this is the Robison plot. It's called Robison plot because there's a scientist, he's L.M. Robison, in 1991. He collected the gas separation data for numerous polymers, and this is from 1991. And he decided that the glassy polymers, these are like the dark black circles. If you see that they have high selectivity, but they are low on the permeability side. And rubbery polymer, it's the other way around. So they would have more and more permeability, but their selectivity would be really, really low. So ideally, you want something where maybe I can use the. Do you see a pointer now? Yeah. So ideally, you want something that's here. So if you have a polymer that's showing high permeability, you also want it to show high selectivity. But that's really, really difficult to achieve because of the microstructure of the polymer and in general how things look like. And again, what do we mean by this? Again, so I'll reiterate the same point, because now you're going to see the same kind of plot throughout the end of the talk, which is the remainder. I have few slides remaining, but so high permeability often means that you have reduced selectivity, and this is a fundamental challenge in membrane science. So what could be the solution? Solution is you design polymer system that can have both high permeability and selectivity. So how do you do it, and what kind of materials and what kind of strategies there are? And that's going to be the remainder of the talk. So I'm going to show you how scientists and engineers have been thinking over the decades to develop materials that kind of pushes towards more high permeability and high selectivity. So one of the best example is inorganic nanocomposites. So what this, or other words, they are just polymer nanocomposites, right? Why do we call organic inorganic? Because the filler that you use, it's inorganic in nature, and the polymer that you use is organic in nature, right? So what happens is you have a homopolymer. So example, you could have a polymer that has a same repeating unit in its backbone, and then you could add different nanofillers, and then the fillers allow you to have different shapes, right? So you could have a cubic filler, you could have rod-like, spherical, mesoporous, irregular. The chances are big. You end up creating a polymer nanocomposite that's usually people refer to as hairy nanopolymers, because once you add these nanofillers to your polymer, you end up creating a structure that looks more like a core shell structure, right? So you have a nanofiller in the center, and then the chains then are grafted onto the surface of these nanofillers, and then they go out of the surface. So if you have a polymer that is a bicomponent in nature, so best example is polymer blends or copolymers, where you have two different kinds of polymer chains, and then you also add a nanocomposite, then you also create structures that are really, really diverse microscopically, right? So like I told you at the beginning, the whole point is you are developing all these better materials to have improved gas properties. And do they improve? The answer is yes. So if you would look here, this is a pure polymethyl acrylate. So here you have a permeability that's around 10, but then the selectivity is high. But you also want this permeability to be high and the selectivity to be high. So if you add nanofillers to pure polymethyl acrylate, then you end up creating a nanocomposite, which is grafted nanoparticle system that has now improved selectivity. I don't know if you can see my do you see my pointer? No, right? Yeah, right. So this is your pure PMA. It has a selectivity that's it has a low permeability but high selectivity, but you want to achieve higher permeability. And once you add nanocomposites, then you push this point to here. So you achieved higher permeability while also maintaining high selectivity. So that's the whole point. And the other way to do is imagine if we could create a polymer that could have voids and in it inherently, right? So that would also do our job, because imagine you have a polymer that has holes in it, and you use these holes for the gas to transport from one end to another. And that's exactly the concept of microporous polymers. So polymers involving microporosity. So this could be achieved using two ways. One, you could have these fancy looking benzene structures that are really rigid. They pack really tight. Because they have this really contorted structure, they pack in a way that's very efficient, and that leaves free volume. And then you could use this for gas separation. Or you could have a polymer that is moderately rigid, but then you could enhance its rigidity by thermally rearranging them. So there are two approaches. And how do they look like? So this is PIM, the classic polymer of intrinsic microporosity. And the structure of this looks like this, right? So you have a polymer that has many, many fused benzene rings. And if you were to look at a toy model in a computer, you would see that there's a hole here, there's a hole here, there's a hole here, because these holes come because the way these polymers pack are very inefficient. And then you use these holes to transport gas when you use them as a membrane. The other way is thermally rearranging a polymer. So imagine you have a polymer structure that looks like, it looks very fancy, right? Because you have a benzene ring, then you have amide ring, and then oxygen and whatnot. And then you treat it thermally. So you heat it around 450 or 500 degrees. And then it also becomes very rigid. And then you can use these structures to transport polymers. And remember, the goal is always to improve their transport properties. Do they improve? The answer is yes, right? So now we have this theoretical upper bound line, and we always wanted our polymers to be here. So when you make membranes of polymers from such structures, you end up having gas transport properties where you have a very high permeability, but also have a nice selectivity that pushes above this upper bound. So both PIM and thermally rearranging polymers do that. So that's one way. And so I showed you two approaches, right? One is you add a nanofiller to your polymer, then you have enhanced gas permeation, then, or you make a polymer that has too many benzene rings or too many cyclopentane rings, such that they pack so inefficient that you have holes in your polymer, and then you use these holes to transport gas, and that also results in a better properties. So what the third approach, it's very interesting. It's called computer generated polymers. And what do we mean by that, right? So I read an article which is very interesting, because if you see this, there were minimum 300 polymers synthesized only for carbon dioxide separation. So this is a huge number. So you synthesize 300 different kinds of polymers only to separate gas, carbon dioxide, because one kind of polymer fails, and then the chemists always try developing better and better materials, because one is really good in gas transport, but it's not stable, or the other way around, or so on. So what we could do is, instead of making 300 polymers in a lab, we could now use computers. By computers, I mean, the idea is, I don't know why my screen froze. The idea is you use machine learning. So what happens is, so you have a synthetic toolbox, right? So synthetic toolbox in here, it just means you have a polymers that has different chemical structures, and then you fingerprint it. It means, so I'll give you a simple example. So imagine you have a polystyrene. So polystyrene has a benzene ring and something in the side chain, right? So you fingerprint it in such a way that you fragment your molecules. So N equals 1, N is 2, N is 3, N is 4, depending on the number of backbones. And then you code them into binary 101 or 101. So very simple. And then you train the model saying polystyrene against carbon dioxide has this permeability. Polystyrene against oxygen has this permeability. Same for all kinds of polymers. And then you let the machine predict and give you a polymer that has high gas permeation properties. Like what I told right from the beginning, the goal is always to have better and better properties. So the machine throws up and suggests you that, hey, if you synthesize so-and-so polymer, then you might end up getting a gas transport properties that is way, way, way above this empirical line. So the machine predicts, and then you again synthesize. So it's a closed loop. So do you guys get it? So you start with the data of already synthesized polymers, you fragment it, you train your model in a computer, and the computer throws you out, some possible structures that can have better gas properties, and then you again synthesize based on the predictions. So this study, which is one of the first of its kind, is so they use 6 gas pairs and 700 polymers to train their data, and they predicted the gas transport properties for 11,000 polymers for the same 6 gas pairs, which is massive, right? I mean, imagine you're predicting gas transport properties of polymers that you did not even measure before. So that's the power of using computers in your in this study. And again, as the goal is always to have better and better gas properties. And now if we look, do we achieve it? The answer is yes. So the computer gave them an idea that if you were to synthesize a polymer that looks like this, so the polymer does not have a name, so they just gave the name that they used for the code. They would say that you would have better improved properties. So the red and blue are synonymous with the structures. So imagine, so this is all your previous data, and now the computer predicted that if you have polymers that looks like this, so P432095 and 092, then you might have a gas transport properties that's way, way above, and then it works, right? So that's the idea. So now you could use machine learning to generate better polymers for gas transport. Now this is my last slide. So there are open questions, as in any scientific problem. So the question is, can we surpass the Robertson limit? The answer is yes and no, both, depending on what you do. So the Robertson limit is this line that you guys saw in this gas transport curve, right? And so this is really nice. It works on a lab scale. You could synthesize, you could characterize and everything. But if you were to employ it in an industry, it's not that easy, because you are using these membranes that are really, really thin, 0.1 microns thick. And if you were to put them in industrial applications, they would most probably have difficulties and they will fail. So that's one of the challenges, right? And then, can we be sustainable? So far we all looked at petrochemical based polymers, right? What would happen if we were to look at bio-based polymers? So that's an alternative. And again, using AI in material science. So we could use machine learning a lot, designing next generation materials with computer modeling. So that's something I'm very, very positive about. And it's really easy. It's a tedious task because it's garbage in, garbage out. If your data is garbage, then what you get is also garbage. So it's a lot of work there. So the summary is polymer membranes are versatile. So as you guys saw, that you can have numerous chemical structures, and they offer low alternative to conventional methods. And the field itself is continuously evolving, and it's highly interdisciplinary. So if you guys were to work in this field, you would work with chemists, physicists, material modelers, mathematicians sometimes, because you are all trying to solve a common goal, that is to understand how the gases pass through the polymer, and when they pass, why does one pass better than the other, and then you're trying to answer this question from a broad view, right? So that's the end of my talk. I hope you guys got to hear something about membranes or polymer membranes in general. And if you guys have questions, then shoot me. So like I said at the beginning, you don't have to remember anything. Just hear 2 or 3 words that polymers are diverse and they can be used in membranes, right? So and that's it. If you have questions, comments, anything, just shoot them away.
So what are the future advancements expected in polymer membranes, sir? For example, what are the future advancements for polymer membranes, sir? For example, using nanofillers or nano additives.
Mm-hmm.
Can you use it?
So the idea of using nanofillers for polymers is very, very old, right? I mean, it dates back to people using carbon nanotubes and adding it to polymers. So nanocomposites is continuously evolving, but the future is more and more towards designing polymers that are inherently microscopic in nature, and somehow trying to maintain its mechanical stability. So that's where the research is more and more headed towards. So nanocomposites, it's for sure it's evolving, but chemists are always trying to think of designing polymers that have holes in them that would allow gas to pass, but at the same time these holes would be sturdy enough to be used in membranes. So that's one of the advancements.
So my question is, how fuel cells and water electrolyzers are used in gas separation?
So if the fuel cell community develops a design that can be used to efficiently separate hydrogen or some other proton from the electrolyte, and if that design is successful, then we could also try to implement that in membrane field, right? Because the principle is same. You're always trying to separate one thing from the another. So if the fuel cell community comes up with a nice design, we would try to adapt it. Very simple.
Students, if you have question on any other thing also, you can ask.
Sir, my question is, after optimizing computer-generated polymers, how do you proceed in synthesizing it, sir?
So that's a good question, right? So when you train your computer model, what you do is you go and collect the data from research articles that are from 1950s there, right? So people have been trying to create membranes since 1950s. So you train the model, and then the computer throws a model that says, if you have a polymer with this fingerprint, like I told you, you have a polymer structure, and then you fingerprint it. So polystyrene example would be fingerprinted into 3 or 4 components, because it has a benzene ring, and then it has some methyl groups that go on the side. So when the machine learning predicts, it throws you a fingerprint, and then you try to convert that fingerprint into chemical structure. And once you have a chemical structure, then the chemists come up with a route to synthesize this, like they did in this paper. So that's how it works. And depending on the structure, it could be really different, right? If it's polysulfones, then they would use synthetic routes. If it's something else, then they might use techniques like raft. I think it's called atom transfer polymerization or something. It all depends on the chemical structure. It all depends on what your computer gives you.
Yeah, now audible.
Sir, apart from the technical prospect, can you indulge us in the master programs, and how can we pursue our masters in Germany, as you were one of the students in masters?
So your question is, how do you pursue a master's in Germany?
Yes, sir.
So it's really straightforward. So Germany has, I think, quite a handful of polymer science programs. So one is in Berlin, one is in Halle and other cities. So you go through their page, you send them your mark sheets and everything, and then you apply with an IELTS. I think, yeah, you need an IELTS. And then the process is really straightforward. So, but the program itself, Germany, it depends on the kind of program you choose. If you choose an applied program, then it's less research and more application oriented. But if you choose a program that's research intensive, then the probability of you doing a PhD is high. So it all depends on what you want to do. Choose programs that you like doing. So, but the admission is really straightforward. You send your documents, you send your grades, letter of motivation, SOP, yeah, then you're done. Yeah.
So after completing, is there any good prospect for job opportunities?
Yes. So people usually have this idea that once you finish a PhD, you become a niche, and then it becomes difficult to get a job. Guys, that's not true. Once you become a PhD, you are employable because they hire you because you cannot attack problem through different perspectives. So if it's a PhD in physics, it's a PhD in chemistry, it doesn't matter. As long as you have a PhD, you are employable. So employment opportunities are really good, even after masters. Yeah.
Okay.
So can you suggest any universities to apply abroad, especially in Germany? Any specific?
So if you want to do science like polymer physics or experimental physics or something, then I would say polymer science in Halle and Berlin is good. But if you want to do engineering, then I think it's more and more towards Bayreuth. So the town is called Bayreuth. I might write in the chat. So you guys know. Bayreuth, it's for polymer engineering. Berlin / Halle for science.
Good afternoon, sir. I'm Kritika, and I'm currently pursuing polymer engineering first year, sir. We heard that you pursued your major in Germany, so we would like to know about the informations to get into research and development field of polymer engineering. So, what are some experiments or projects you would suggest for getting into research and development?
Research and development, where do you want to get into research and development? Where like back home in Chennai, or do you want to go? Where do you want to do it? All depends on where do you want to do research and development. So I would say, since you're in first year, that's very motivating that you're interested in this. I would say start at the university level, talk to your faculty. I think the faculty in polymer engineering does excellent research. So start with them, get hands-on experience at laboratory level, and then maybe also try to do some internship at national labs. I think there is NCL in Pune. So NCL in Pune is really big. IIT Madras has excellent summer fellowship programs. So look into this, and that's your first steps into getting into R&D. And that's way better than getting research and development experience in industry, because it's completely different. If you work in a lab in the university or NCL, you will learn a lot. So the idea is be open.
Okay, sir. Thank you. And also, I would like to know about the stipend for major in German. What would be the stipend? Masters.
For masters, you don't get a stipend because masters is a regular degree. But if you do a PhD, then you get a stipend, and because engineering PhDs are paid well because they are 100% contract. But if you do a PhD in physics, it is also paid well. So it's 67% of your regular salary, but you can live comfortably with that if you're alone. So you don't have to worry about the money.
Is there any way to get into aerospace with polymer engineering backgrounds?
Yes. If you work a lot towards composites and mechanical testing, then aerospace industry opens up, and it all depends on the positions that are opening up. I think in India it's Suzlon, right? Suzlon is the company that makes wind blades for aerospace applications, and there's Insigner Plastics. I think a batchmate of mine, Arvind, works there. They sell polymers for aerospace industries. So you can look and contact them, and they might, if there's something, then it might be useful, right? be open. Don't restrict yourself to aerospace industries. Research is broad.
Thank you, sir.
Yeah.
Sir, I'm doing my first year in polymer science.
Mhm.
Actually, I have two questions. First one is to study German language. Which level of German would university prefer, sir?
So B1 is minimum, but B2 is best. B2,
Okay.
yeah.
And another question: studying in Germany, if we want to do part-time job, which
Yeah.
which would be preferred to maintain both work and educational balance?
That would be to work as a student research assistant in any of the research labs. So that's what I did. So you can, so you don't have to get into the kind of research that you want to, but if there is an opening, just go. You could be a polymer engineer, but if there is an opening in a chemistry department, just walk in, work there, and it will pay you something, but you will also be in touch with your studies. So that's the best way.
Thank you, sir.
Yeah.
Sincerest gratitude, sir, for an intellectually stimulating lecture. Your profound insights has been truly impactful, providing us with a novel perspective and rekindling our motivation to pursue our aspirations with renowned vigor. Indeed, gratitude is the most equivalent form of appreciation. I now invite Mustaq Naina from third year to offer a vote of thanks.
Good afternoon. It's my privilege to propose a vote of thanks on behalf of Department of Polymer Engineering and Association of Polymer Engineers under School of Mechanical Science. First and foremost, we express our sincere gratitude to Almighty for His blessing in bringing us together today to share knowledge, celebrate achievement, and strengthen our academic community. I also take this opportunity to thank our Dean School of Mechanical Science, Dr. Aejaz for his continuous motivation and guidance towards all our department activities. A special note of gratitude in our beloved Professor Dr. Abdul Majid sir for being a constant source of inspiration and encouragement. Our sincere thanks go to our head of department, Dr. Samsad Begum ma'am, whose leadership and unwavering support have been backbone of our success. We also extend our deep appreciation to our faculty coordinator, Mrs. R. Daulat ma'am, for her tireless effort in making this event grand success. I would also like to thank our faculty members, Dr. Basantakumar Behra sir, Dr. J. Shahida Varveen ma'am, and Mrs. J. Daphne ma'am for their valuable guidance in organizing this event successfully. A special thanks to our student coordinator for their relentless dedication and efforts in making this event possible. Last but not least, I thank all my fellow students for energetic and enthusiastic participation. Your involvement has made this event truly memorable. Thank you.